under Newton's laws of motion and the related forces, the related things that play their role in computing and calculating the forces that act on a fluid flow situation. So momentum is another important thing that needs to be considered and evaluated and see what role it is playing, how much it is present in a motion. So we need to consider that. And as we know that if the force is F equal to ma, mass into acceleration, according to the second law of Newton's law, then which is written as given here as equation 6.13 here, the moment or momentum is considered to be mass into the velocity. But here this is acceleration, so this can be compounded as the rate of change of momentum. And sometimes, well, m into v is called as either only simply momentum or linear momentum because it acts linearly. So noting that both the density and the velocity may change from point to point within the system, then the Newton's second law, the same law that is written here in this equation, can be written in the integral form, and when we integrate it over this system, then the variation of rho will be, that is the density, will also be taken care of. I have already mentioned that these numbers of these equations that are referred to here, sometimes that occur in our discussions, they are the same number of equations that you will see in the book that we are following, Fluid Mechanics by Simbala and Sengel. I have mentioned that many times. So if this kind of reference occurs, it is understood that they are referred to the book. A small change in mass can be written as rho into d into volume. Remember, the density is defined as mass per unit volume, and from this a small change in mass is represented here. And the second law, of course, is Newton's law. We have mentioned and discussed it many times, but we can write down the equations in this form that d by dt of m of v over the system is equal to, and it is written in the integral form so that the variation in the density and the other things can be taken care of if there is any change. But in most cases, if the rho is constant, if the density is constant, then it can come out of the integral and it can be treated as constant. So the same thing is written in the descriptive form, and for a fixed control volume, the summation of forces can be written as d by dt of this quantity, that is the integral of the momentum. This integral is taken if the density is changing, and so this is control system and this is control volume. So the two things have to be taken care of if we want to calculate all the forces that are occurring there. We make use of Reynolds transport rule or theorem that we discussed some time ago, and the same equations are shown here. Even the same way of methodology is exactly the same, and I have discussed this with you already. The linear momentum equation is obtained by replacing B in the Reynolds transport theorem by the momentum mv. So momentum is defined as mv, and capital B is replaced by small b by the momentum per unit mass v. This picture, which is of the form of a small elbow, it shows what kind of forces are acting at different places. So there is gravitational force, the reaction force, atmospheric pressure, there is P1, there is P2, or gauge pressure if we level out the atmospheric pressure, but in a fluid flow situation, when the fluid is flowing and distances are different, then it can change. The momentum equation is commonly used to calculate the forces, usually on support of systems or connectors introduced by the flow. The flow in pipes, the flow in any containers considered, and again for a control volume which is shown here by the red dotted line, shows the forces that are acting when the flow takes place in this situation. In most flow systems, the sum of forces, summation of F, consists of weights. The weight is the main thing, the gravitational force that is acting, plus the pressure force, and indeed the reaction to the pressure that comes with it. Gauge pressures are used here since atmospheric pressure levels itself out, that is, it is the same everywhere, and therefore the total summation of forces is as shown here, and we have discussed it. As a special case of this, if the flow is steady, then obviously what will happen? Earlier, when we were writing the total forces, then there was this force plus d by dt of integral of similarly another term. But that term turns out to be 0 because the flow is steady, so no motion with respect, no contribution with respect to change in time. So d by dt of whatever is being changed or considered is 0. And this happens only when we are putting the restriction that the flow is steady. And then this is the value that we will get for momentum flow rate across a uniform inlet or outlet in a similar flow situation as was shown in that elbow, or it can be a pipe and similar gadgets. In a typical problem, the control volume, earlier I just show you a picture in which there was an elbow and there was one inlet and there was one outlet. Fluid flowing in from one side, moving out from the other side. But here, as the picture says, there is a possibility we can come across with a situation where there are more than one inlets and more than one outlets. So we each add up all of them as indicated here. And it's a simple algebraic summation, so no big problem. And similarly, there are 3 situations here again. There is a control volume, fluid flowing in this situation A, and we consider the velocity V average here. In B, another situation is being shown. You can see the fluid is coming from in a wider range and then choking in. So velocity is going to change. Pressure terms will also be changing in a pipe. And therefore, in the first picture, you see that it is a well-rounded pipe in which the fluid is entering. In the second one, it's a wind tunnel, and for designing many things, for testing many things that we make, and we want to see how the fluid flow, just to see how much drag is there, how much heat will be developed, and so on. So they want to design and test it, and therefore, so this is a wind tunnel where they test it, and this is a free jet air in a nozzle. So you can see that the nozzle area, the outlet, is being reduced as compared to the entrance point. The velocity will change, pressure terms will change, but we need to consider them according to the situation.